All right. Hello, hello. Guys, I'm so sorry about last week. I I feel terribly. Somebody emailed me, I think it was even the next day, and that's when I realized my email hadn't gone to you guys as well. So did you guys just sit here waiting, or what'd you do? 45. I'm so sorry. Good. So I don't blame you. Feel free to email me, by the way. Um, but gosh, I'm so sorry. I never thought I would stand up a class like that. I was headachy and not quite feeling up to teaching, but I was just sitting at home resting. So I thought I had emailed you. I just so sorry. Um, so I'll see if I can make that up to you somehow. Um, okay, so today I want to quickly first talk about kind of where we are with the syllabus and stuff, see how I'm going to try to catch up with things for you. So we've had 2 canceled classes now. So normally I would do an exam review in a class period, and I think I'm going to try to do that outside of class period, virtually most likely. Possibly could reserve a room and do it virtually that way. So that's TBA. I haven't decided exactly when or where. Happy to have input. How many of you guys attended virtually on Thursday last week? Okay, and how many of you went back and took a look at that later instead? Anybody? Okay. Did you find that useful, helpful? It's a pretty good way. Nobody actually interacted with me, but you're welcome if we ever do that, like if we do this review online. If it's live, you can comment and I'll see it right there, and your classmates can see it, and I'll respond to you in that way. I think there's about a 10-second delay, so feel free. We have 2 viewers online right now, may or may not be the class. So even if they were to say something, if I look down, I'll see it. So feel free to, if we do ever have that situation, or if you're out sick or something, please feel free to ask questions. Okay, so I'll let you know more details about that. Please do give me some feedback if you are really concerned about that or whatever. But that would normally be the time, and I think I have probably one scheduled for, before the next exams, where I would go through the solutions to the homework. I go through questions you may have about the exam, things like that. So what I'll try to do this time is keep the exam where it is, pending no other cancellations. Happy to have COVID out of the way, so probably don't need to cancel anything else. I'll reserve a bit of time on the 21st to talk about the exam directly, answer questions you may have about kind of formatting, things like that, and then save the rest of that for the exam review session. Okay, so with that then, we're going to wrap up just a little bit about mass balances that we left off on last time, and then dive into some chemistry, maybe even getting into kind of the intro to drinking water treatment. If we go fast enough, maybe we can just get ahead of the game and have the exam review like normal. All right, any questions? Okay, feel free to suggest at some point how I can make up the bailing on you last week, if you think of something. Okay, so this is where we left off on Thursday with the online class. We were talking about setting up mass balances. We went through a couple of examples for some of the more common ones, but I was telling you I'd like for you to be able to set these up from scratch. And so we have an example for you to do just that. So I'm going to give you a couple minutes. I'll read this through with you and then give us some space to work through it. But I want you to take a few minutes to, at minimum, try to set up the mass balance itself. And what you'll see here is that if we think about the prior lecture, we said, okay, we've got these inputs, the outputs, and the reaction. We are, in the problem, you'll see we're given steady state. So we know something about how to paint the big picture. And what you'll notice is there's key pieces of information in the word problem that clue you in. So I'm going to help you guide you through a few of those and see if you can assemble this mass balance. So, well, let's read it first. Consider a 10 times 10 to the 6 cubic meter lake fed by a polluted stream having a flow rate of 5 cubic meters per second and a pollutant concentration equal to 10 milligrams per liter. And that's this figure here. There's also a sewage outfall that discharges half a cubic meter of wastewater having a pollutant concentration of 100 milligrams per liter. The stream and sewage wastes have a decay rate coefficient of 0.2 per day. Assuming the pollutant is completely mixed in the lake and assuming no evaporation or other water losses or gains, find the steady state pollution concentration in the lake. All right, so we already kind of have a drawing here, but it might help to make your own, just to conceive of it yourself. Here we have 2 inputs and 1 output, so we already see something a little different than the cases before. We have some sort of reaction, and we could go on labeling each of these pieces if you wanted, but the figure's already got it for you. Take a minute and remember what we're looking for is some accumulation term is equal to the input rates. So it's really an accumulation rate equals the input rates minus the output rates plus any growth reaction minus any decay reaction. Sometimes we'll just write plus reaction and you fill in as needed, but this would be the expanded way to say it. And this would be the growth rate or decay rate. So see if you can put that into math and start solving. I'll give you a few minutes and then help you. so I'll pause you here and point out a few things. First of all, we were told this is completely mixed. That means we can treat it pretty much like our CSTR rather than a plug flow. If it was not completely mixed, then maybe we have to do something different. But the completely mixed condition means we can treat it like a continuously stirred reactor. It's got some volume. We've got two inputs. We know that. So we've got two flow rates that are going into the input. That would be our Q from the stream and the Q from the waste. Got one output. That's our CM and QM, and we can do a quick mass balance on water to say, well, 5.5 cubic meters total are coming in, so that means that much is going out, right? We were given 5 cubic meters per second in the stream, half a cubic meter per second in the sewage outfall, so 5.5. The other potential trick here is it gave us a rate constant for our reaction called a decay coefficient, and it described it by just simply saying it's 0.2 per day. So you have to think back on last time and remember that when we want to know our reaction order, in order to know what N goes into our reaction term for when we slot it into our equation here, there's some question mark there. The way we can know that just by given the units is it has to satisfy the same condition regardless. The dC dt, that's a mass per concentration per time. That's always has to be satisfied on the right side here when we have a K times C to the N power. So if we have a concentration per time and then our units for K is per time, then all we need is concentration. N has to be equal to 1. Concentration to the 1 power is concentration. So that means we have a first order decay reaction, so that's why we put in our reaction term in that volume. It's K times C to the 1 power. All right, so with that, hopefully you should be able to see, and then the last piece here saying that it's at steady state. That means our accumulation goes to 0. We've reached an equilibrium point where the system is processing stuff, but it's reached a steady condition where we have a constant amount coming in, constant amount going, constant amount being destroyed inside of our lake. That means once we've given that enough time, the concentration should hold steady. So that means 0 is our accumulation term, equals the inputs, the QSCS, plus the other input, QWCW, minus the output, QMCM, minus this decay reaction inside that volume, VKC. Does that make sense? Any issues getting to that? All right, so take a minute then and see if you can find the answer solving for what we're looking for. In this case was CM, right? I'm going to go ahead and write that up again. There's one little trick here. I'll just call your attention to it now. We have CW, CS, CM, and just plain C. And that could get you confused here, and I'm going to go ahead and clarify that. Remember, we said that this lake is completely mixed. That means as soon as something's in here, that's exactly the stuff that's leaving, right? So as soon as we get it completely mixed, which is instant, according to our assumption, then whatever is in here is the same stuff that's leaving. So C equals CM. Okay, that's just a fact of the situation where we have a CSTR. So that means up here we can write this as CM. Okay, give that a shot. It's just algebra from here. All right, so anybody get an answer yet? Yeah.
Do you not have to convert K to seconds?
You absolutely do. Good catch. So what you'll notice here, if you did try it and come up with an answer, if you didn't notice that K is in days, you'll need it in seconds, right? And so this is why I really highly recommend, maybe you go through a solution like this and you write it up with the letters. The first time you go through and write it up with the actual numbers, I recommend putting in your units so you can visually see exactly what you just pointed out, is that right here on the denominator, we need cubic meters per second. So we have this cubic meters per second plus this cubic meters multiplied by something, hopefully would give us per second, but it's giving us per day. So that we can't actually add those together realistically. So we have to convert first. But otherwise, we can see it on the numerator, we've got cubic meters per second and milligrams per liter, all in one unit, and cubic meters per second times milligrams per liter, all in one unit. And once we divide by cubic meters per second, then our units will come out to be a nice, clean milligrams per liter, assuming we do everything correct. So here at the bottom, we have to multiply by, I think it's 1 day per 86,400 seconds, something like that. And so if you do that, since I did this morning, this should be 3.49 milligrams per liter. All right, make sense? So now we've gone from this mass balance approach, built up a mass balance equation, and solved for the thing that we needed, right? And you can imagine if you're given the information, but a different piece is missing, maybe you had the final concentration, but you didn't know how much waste was in the outfall, you could solve it for that, right? It's actually not a different process, it's just a little bit of different arrangement of the algebra. So what you are now equipped with is a process to get your answers for a wide variety of systems. Okay, so that's going to be fundamental to many of the units we cover. So I really hope you take the time to familiarize yourself with this approach, whether it be first order, zero order, growth, decay. We're going to be seeing this a lot. Okay, so one quick note before we get to the chemistry directly. Sometimes we might have actual data, and we want to know something about the rate constant given that data. The most common way to do that would be to take some batch reaction where we could describe it as dc dt in that volume. It's mixing, and we just track to see what happens to that concentration over time. So that would be, maybe if it's a zero order, we just see something like that. Or maybe we have some reaction that we're getting data and it looks a little different. And let's just say it looks something a little more like that, probably a first order. So depending on what situation we have, we can use essentially a line of regression to solve for what we need. So in a zero order system, when it's dc dt equals, let's say in this case a minus k times c to the 0 power, well, the slope then is k, right? So we just find the regression, get the slope, we're done. In a first order situation, we can't just grab a slope from that. So what we can do is linearize the data. We can take it over to Excel and plot instead of the concentration. And we already talked about this a little bit, but I didn't talk about it in the sense of finding a K. So I could pull out Excel in a moment if you'd like, and we could plot the natural log of C over time, or perhaps we could do concentration over the initial concentration, and then that will plot it like this, do a line of best fit, and then that slope is K, where we could write it as the natural log of C over C naught equals minus kt. That's the form. That's y equals mx. Of course, we could write it as natural log of c equals natural log of c naught minus kt, and then that's mx plus b, but this is just the simpler way to do it. Okay. So that's pretty convenient. The other thing to note here is if we have a half-life. Half-lives are commonly used, especially in radioactive decay kind of systems. That's because radioactive decay is a first-order decay reaction. It's going to be disappearing in accordance with how much stuff is there in the first place. And so since it's first order, it kind of works out pretty nicely that we can say, well, the time at 1/2, that's our half-life, is the time when c equals 1/2 of c naught, what we started with. That's very painfully obvious, right? So we can rewrite this as c over c naught equals 1/2. Obviously, maybe we start with 100 and then c is 50 at our half-life time. We could do it a quarter life, but no use doing anything different than half-life in most cases. But you could, right? You could do an 80% life. How long does it take before we get to the 80% mark? Any of that's fine, and the key thing is for a first-order situation is that these are relevant and relative in such a way that when we do our ln of c over c naught, that's minus kt, so first order. Let me write this. Half-life is going to be most often for first order. Then all we have to do is say ln of 0.5 is equal to minus k times whatever value we know is the half-life value, right? If it takes 5 minutes for it to decay by half, then we have 5 minutes. So then we can solve for k very easily. K is negative natural log of 0.5, just some known value, divided by the time it takes to get to 1/2. Okay, so you can solve for k, and sometimes you'll encounter a problem that talks about how long it takes for the ozone to decay in a system, and it's half the amount by this amount of time. You'll see sometimes that it clues you in on how to solve for your rate constant by giving you some information. Okay, this is stuff you've seen before, so this is not particularly new. Just reminding you a couple of ways to get the half-life here, or to get to find the rate constant. You've done lines of best fit in Excel, I'm hoping. So linear regression. So if you just convert the plot from a c to a natural log of c, then you can get that for the first order. Probably won't be doing a whole lot of that. I just want to make you aware. This is pretty common stuff. You'll see it here and there. You'll probably see it in completely different contexts. You could do this, like I've said a few times, in banking or accounting in terms of investment. All right. So I think I drew all of that on here, basically. So if we were to do a linearization, c over c naught, it would just look more like this. All right. Okay, so that's it for this set of slides, and we'll go to the next. All right. So we talked briefly about this when we were talking about units in general. So today we're going to go in a little bit more depth. We're going to touch on chemical equilibrium. So we'll deal with a little bit of that with pH and chlorine. So quick reminder, here's our element. So our atom of oxygen here. The top number here, this is just the number in order of which it appears on the periodic table. So it might be the atomic number, I guess you'd call it. Here is our atomic weight. So that's the one we're more interested in for the math that we need to do typically. So the atomic weight of oxygen, or atomic mass, is about 16. And remember, this is, we could call it atomic mass units, AMUs, but realistically what we say is that's 16, so that's each atomic mass unit, one atomic mass unit is 1 gram per mole. So oxygen then is 16 grams per mole, right? Okay, so then we put a bunch of oxygen together. Let's say O2 is, the molecular weight for O2 then is 32. Molecular weight for ozone, which is O3, is 48 grams per mole, okay? So when we talk about oxygen during the class, a lot of times we'll say, let's say dissolved oxygen, or such and such combusts and reacts with oxygen in the atmosphere. Typically what we're talking about when we're generically talking about the oxygen we breathe and that dissolves in water is molecular oxygen, okay, O2. Now, ozone is also a form of molecular oxygen, but we will specify if we are talking about ozone because it's much more reactive. It's harmful to your health. It disinfects bacteria pretty well. So breathing ozone is a little bit like breathing gas phase bleach in some sense, right? You don't want to breathe a whole lot of it, which is why if we have a lot of smog, air pollution, we're essentially breathing in an oxidant that's an irritant, and that can cause us a bit of harm. So typically we'll be talking about oxygen as O2. Of course, there is oxygen, the atom, which would be the 16 grams per mole. Okay, makes sense? And just a quick reminder here, the subscript after an atom, that's talking about how many of those atoms are in that particular molecule, or at least in that little grouping. So speaking of, we have some common ions you'll see. I don't really care too much if you memorize them all. I suspect that you probably should memorize a few of these that are the more common ones, especially if you're planning to do much chemistry ever. Well, first of all, we've got some atomic ions. We've got hydrogen, sodium, calcium, chloride, bromide, iodide. Obviously, there's more, but these are reasonably common. You'll find in water systems. Then we have molecular, or what you could call polyatomic ions, right? The dreaded thing back from general chem. So phosphate would be the first here. So these are phosphate ions. So PO4 3- is phosphate. I don't really care to get into the reason it's 3-. Probably just be easier for you to skip that part and just remember, if you're going to that phosphate PO4 is a 3-. One thing that happens with these types of polyatomic ions sometimes is you add an acid group, an H+. And when you add an H to it, it gets rid of one of the charges. So now it's HPO4 2-. Goes to H2PO4-. And it even goes to H3PO4, which is no longer an ion, but it's still part of that same system. And essentially we have equilibrium reactions, which we'll talk about in a moment, that go back and forth between these states. Depends a lot on how much of the H+ is there. That's acidity. So this is a pH-dependent process of how much are you going to have in the PO4 3- versus the H3PO4. So pH is going to impact these. Even pH goes through that water with this OH- and H+. This is acid-base chemistry. We're going to have to deal with a little bit of that. Okay, we also have sulfate and sulfuric acid here. So H2SO4 is what we would call sulfuric acid. And we have HSO4- kind of in between the sulfate and the sulfuric acid. CO3 2-, this is carbonate, also known as CO2 that dissolved in water. So this is basically CO2 that's in the atmosphere, dissolves in water. It actually reacts with water. CO2 plus H2O you'll notice combines directly into having 3 oxygens and 2 hydrogens and 1 carbon, right? So we just kind of write it a little differently, but once it dissolves in water, then it can lose a proton and become what we'd call bicarbonate, HCO3-, or carbonate, CO3-2-. And then, of course, we can send it the other way and let it back out into the atmosphere as CO2, because this is what we would call a reversible reaction. Now, anybody have a soda here? Like a bottle of Sprite or anything, Coke, whatever. If you did, and it has a lot of bubbles in it, that's actually carbonate, right? It's a carbonated beverage. And part of the reason why we like to serve it cold is because gases dissolve typically better in colder water. So if you warm it up, let's say if you put it in the microwave, all that gas is still in there, closed into it, and it's going to want to be outside of this liquid now. It's going to try to fill up that headspace, and that's going to build up a lot of pressure until it goes boom. So don't do that. The other thing is you could change the acidity. If you were to suddenly and drastically bring the acidity, they typically sell it pretty acidic. That also helps you keep it in a form close to here. And if you were to change the acidity, that might also change how much is able to stay in the typical condition. Okay, so in that might be, I'm not sure about this, I think maybe not, but that might be part of the reason why dropping the Mentos into Diet Coke or whatever causes a big reaction. I think there's more to it than that. Anyway, some chemistry there that you may or may not have known about. Water can ionize into OH-, so hydroxide, and H+, just hydrogen atoms, or acidity. That's going to happen with an equilibrium reaction. And then there's a few others, common ones here that typically these guys, the nitrate, NO3-, NO2- is nitrite. Those two don't typically pick up the hydrogen. They don't really have acid-base characteristics. OCl-, this is hypochlorite, so this is chlorine. This one does go back and forth with HOCl, and we'll talk a lot about that. Another pH-driven equilibrium that is relevant to our disinfection. So mostly I want to familiarize you all with this. I'm going to give you a page of homework to kind of fill in some of these as a refresher. That's going to be optional, completely optional. I mean, most of the homework I'm going to be looking for completion and to see that you tried it. For that one, if you want it, if you need it, go for it. If not, no problem. Okay, next up, stoichiometry. So this is how we compare our chemicals to one another on a number of molecules and number of atoms basis, right? We talked about the silly example of egging a car, right? This is when we compare numbers to numbers, because chemical reactions happen on a numbers basis, not on a mass basis. So whenever we're comparing chemical reactions, something reacting with something else, we are always on that numbers basis, meaning we need a molar basis. So moles per liter or moles of stuff. So an example here would be methane combustion. So CH4 reacting with oxygen in the atmosphere. This will happen pretty easily if you have the mixture there and you give it an ignition source. If you have a gas stove or a gas lamp or anything at home, this is happening quite often. Be methane or propane. And then what you're going to get is some amount of CO2 and some amount of water. If it's like, the ideal perfect reaction. So the way to go about balancing a stoichiometric equation here is what we're looking for is, well, how many molecules of methane react with how many oxygens, and then what's our resulting number of CO2 and water. And typically we can find all of that just by sorting it out, try a little bit of trial and error to see, well, what makes this equation balance? We just need a numbers balance on the atoms. So we're not going to create or destroy any atoms because we're not doing nuclear physics or chemistry or anything. So what we're going to do is say, well, let's just default start with the carbons. That tends to be simple. And I'm just going to default to 1. We can change that if we need to later. Maybe we'll double it if we had to. So 1 carbon over here on the left side of the equation, and I'm going to match that and make sure there's at least, or there's the exact same number of carbons on the right side. So for each of the carbons, I'm just going to default to a 1 and have that as a starting place. Okay, so then I'm looking for another atom to balance. I balance the carbons. And now I'm looking, well, there's oxygen in the 3 others. There's hydrogens in 2 of the others. So maybe it would be easiest to balance the hydrogens first. We've got 4 over here the way we started. So that means we need 4 over here on the right. So I'm going to go ahead and put a 2 for the waters, right? Because we have 2 molecules of these waters, and each of the waters has 2 hydrogens. So that gives us 4 hydrogens there. And now I can go back and balance the oxygen, which turns out pretty nicely that that's the only one open. And we're going to be told basically by the right side of the equation what we need. So we've got 2 oxygens here and 2 here. So we need 4 on the right side, meaning we have 2 oxygens there. Okay, make sense? All right, we're not going to do anything too crazy with this kind of stuff, but you should be able to do that. So again, you'll have a little bit of practice on the first homework. We'll get that posted probably later this week. Okay, so now let's take that and apply it. I'm going to have you try this for a moment. We have a question about what mass of CO2 is produced if 100 grams of butane, C4H10, is fully oxidized. So fully oxidized meaning we go from butane plus oxygen to CO2 and water. So give that a couple minutes, make sure you can do that without any issues. And what you'll see here is we have some known mass quantity, which is relevant to our human existence. It's easy to weigh something or know something about that. And we need to send it through this chemical reaction and find some mass quantity after comparing it on a molar basis. All right, so you see I've written up the solution here so you could follow along if you were done. So first of all, before I even started anything, I knew I was going to need to be converting from mass to moles with butane and with CO2. So I went ahead and just did that calculation. C4, that's 4 carbons, each at about 12. That's going to be 48 plus 10 for the hydrogens. That's going to be 58. Yeah, did I do something wrong?
I think you might have put 2 moles of butane instead of 1 mole for the conversion. I put down.
For right here.
Yeah.
Oh, yeah. Thank you. So it should have been 8 here. I looked. So I was going to explain this in a moment, and I confused myself here. I looked here when I should have looked here. Okay, so I wrote out the molecular weight, and so this is obviously wrong. We'll correct that in a second. Thank you for that. Okay, so I got the molecular weights. We had 58 and then 44 for CO2, 58 for butane. I just went ahead and put those down. Next thing, I went to the stoichiometry, and I started with 1 carbon, or one of the CH4s. Started with the carbons. That meant 4 CO2s. Did the hydrogens, that meant 10 on the left, so 5 on the right for the waters. And then for balancing the oxygens at that point, we had 13 on the right, so 5 here and 8 here. That means I would need 13 divided by 2. You can leave it that way, that's fine. What you probably shouldn't do is what I did and have both written at the same time, so you don't confuse yourself. The other thing you could do is multiply everything to just get rid of the fractions, right? Some people like to say that that's the way you should do it, is have everything as fractions. So you can just multiply everything by 2 and have those up there. That's fine. Either way, you know, it's going to make it's going to be the same difference whichever way you use. So then the key here is when you go to convert, to compare the butane to CO2, what we're doing is a comparison of 1 molecule of butane yields 4 molecules of CO2, which is a little self-evident because there's 4 carbons here. If they're all oxidized, each making a CO2, you maybe could have known that before without even doing the stoichiometry. At any rate, that's the stoichiometry, and this is the way to do it. And so what we see is now we need to convert from this 100 grams of butane into how many moles of butane is that? How many molecules are there? That turns out, if we take 100 grams divided by 58 grams per mole, that gives us 1.72 moles of butane. And if you write out your units here, it will help, because you see I write out moles of butane per grams of butane, and then I see the grams and grams cancel, we yield moles. And then in the next part, I can say 1.72 moles of butane times this ratio, and this is where the stoichiometry comes in. It tells us the ratio of how many CO2 on a numbers basis are we getting per number of butane. Right? So that's why we needed the stoichiometry in the first place. I did this wrong when I did it. I said 4 divided by 2. It needed to be 4 divided by 1 or 8 divided by 2. And so anybody have a correct answer for me here? How many moles of CO2 are we using? So we'll say 5.94 moles of CO2. And so we can take that 5.94, multiply that. So we have, again, writing out the units, moles CO2 multiplied by grams CO2 divided by moles CO2. The moles of CO2 will cancel, and we'll be left with a gram CO2. Right? So even if you get lost in the chemistry, just think the units. Okay, so that gives us what answer? What'd you get?
It's 6.8. 4 moles, 6.8.
Okay. 302. Okay. All right, no problem. Glad it's not just me making mistakes, right? Okay, so there we have it. That would be then your answer for the problem, right? Okay, any issues, questions with that? Okay, hopefully straightforward review. I just want to make sure I give you this review so you are familiar, you're comfortable with it. And by the way, feel free to practice. You can think of different molecules if you just look up some generic hydrocarbons. You could do propane, you could do methane, all sorts of different ones. Of course, there's plenty of general chemistry reactions. Oxidation reactions like this are a pretty straightforward deal. Okay, those oxidation reactions are good examples of irreversible. It's really difficult to convert CO2 back to something like methane. We got to send it through photosynthesis or some elaborate process to get there. Probably requires a lot of energy. It's just such a different amount of energy that's stored in a carbon that is not oxidized compared to carbon that's oxidized. It releases so much energy. That's why we have an explosion. That's why we get usable energy out of it. So that would mean that reaction really realistically cannot be reversed. Now that's in contrast to reactions that are reversible, meaning there's probably reactions going in both directions simultaneously all the time. So for example, my bottle of water here, I guarantee you there are H plus atoms in here, or ions, and OH minus ions in here. And they're constantly reacting with one another to make water. And water is constantly reacting to dissociate to form OH minus and H plus. Most of it's water, as we'll see, but that's ongoing. That's just happening all the time, no matter what. So those would be reversible. There's not really a big energy difference in one state or the other. And it's kind of two reactions going in either direction. So one thing that happens here is we get what we could call partial ionization. When I say ionization, I just mean going to the ionic forms. So for example, under most circumstances, sodium chloride dissolves in water to give Na plus and Cl minus. Usually, unless we have a whole lot of NaCl, this is completely ionized. So we would say sodium chloride, when you put it in water, under normal conditions, completely ionizes. We get seawater with, an equivalent of like 20 to 30 grams of sodium chloride in every liter. Now, if you were to go way crazy and find the saturation point, that is possible, and technically you will find a reversible reaction with sodium chloride as a solid. So we'll say super high saline. You would have partial ionization where we have NaCl, kind of like our table salt, as a solid in equilibrium with Na plus and Cl minus. So sometimes we'll have cases like this where under most scenarios it completely ionizes. Or you'll see a word problem that says we dissolved sodium chloride or whatever and it completely ionizes. Sometimes we'll talk about different acids in this manner. That tells us that we're not expecting to have the parent molecule anymore, and we can treat it like an irreversible reaction. So be paying attention for these scenarios where it's either partially ionized, some of it's in a non-ionic form. This is bleach, by the way, HOCl, or hypochlorous acid. And some of it's in the form of H plus and hypochlorite, which is a weaker form of bleach. So in the case for disinfection, when we want to use bleach, actually this guy's a little bit more important, or a lot more important, so we tend to try to balance our pH to make sure that most of it's in that non-ionic form. So when I say ionic or ionized, whatever, this is really all I'm talking about. Some situations will have partial ionization, partial, like it's in equilibrium. We have a forward reaction for this bleach, the hypochlorous acid, going forward to form H plus and OCl minus, and those two can react with one another to go backwards and form HOCl. That's an equilibrium reaction. we reach an equilibrium when these rates become equivalent. Now, that can be balanced one way or the other. It could be that we have a very small amount of OCl minus, but the rate at which it goes backwards is pretty high. So even though we have a lot of HOCl, the rate of it going forward is pretty slow. The net rates become equal, and I'll show you a video demonstration of that in a moment. We eventually find an equilibrium, is the point. And that equilibrium point is going to shift based on sometimes the pH or just the nature of the things. A lot of times that value is a bit temperature dependent as well. All right, so here's this video. Let me pull it up for you. Maybe. Let me just do this a moment. It's not behaving. Some sort of that. All right. All right, so let me see if I've got the volume going. All right, I haven't tested the volume yet, so I apologize if this is actually, let me test it right now. Okay, sounds good. All right.
Okay, this little demonstration kind of helps us with the idea of equilibrium and reversible reactions. So what we see here, to start off, we have colored water, so green water here, that represents our reactant side of our process. And then of course we have our empty container over here that represents our product side of the process. So in any good reaction, when you start the process, everything's a reactant. So we all have all the water over here, and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on our very first scoop, if I'm using two identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product, and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now if I continue to scoop like this, and continue to do this, you'll notice how at first the reaction ran really fast. And at first, a lot of water was switching sides, going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here, I only have 200 on this one, so I'm not quite there yet. Okay. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, and again, this is not perfect measurements, but if we look at our volumes there, they're almost identical, which is showing that the amount that's crossing from here to here is equal to the amount going this way. Now the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay, so the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. Okay, so if we go back to the graph on our slide, we would see that this is the first one, or the top one, where the rate flatlines and becomes equal. Okay. Now, it doesn't mean that we have to have equal amounts. If we look at our tubs, because I was using the same size beaker, the volume level in the tubs are also very similar. So you'd almost get the indication that maybe the amount in each side has to be equal. So it has to be 50% this, 50% that. And that's not necessarily true. If we reset our setup here, and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. Okay, so in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay. Now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volume, which means if I pour 140 into here, and I pour 140 into here, there's no difference, okay? So
All right, so that's it's a nice little video to kind of illustrate the equilibrium reactions in some sense. And you notice that the equilibrium is not about how much is there, it's about that rate of transfer, okay? And it was also a decent illustration of before you're at steady state and then reaching steady state in some system, right? So at some point there was, you reached a steady state in both conditions where the amounts were no longer accumulating one way or the other. Even though there was stuff happening, transfer in and out, whatever, it reached a steady state eventually. So we can think of equilibrium reactions in some sense as conditions that will reach steady state. For the purpose of our class, I'm not too interested in the time before we reach equilibrium. We just need to know how to handle a situation that has reached equilibrium. Okay, so now the way to do that from a mathematical point of view, or connecting this to our stoichiometry, is in the following manner. First of all, we'll label the stuff on the left side of a reaction as the reactants and the stuff on the right as products. And then we can write a typical equilibrium reaction like this, where we have some lowercase a number of molecules. This would be like 1 CH4 plus 2 O2, the 2 being the small b, the B is the label for oxygen. That's the type of equation I'm talking about here. So this is our stoichiometric equation, and it's saying we have A number of A molecules or atoms, B number of B molecules, C number of C molecules, and D number of D molecules. And then, with that labeled out that way, we can describe an equilibrium constant as an equilibrium value, capital K, equilibrium, is equal to the products as expressed in a molar basis divided by the reactants. And more explicitly, the way we'll say that is the concentration of C raised to the C power. And remember, the brackets refer to moles per liter of X here. So always, always the brackets means moles per liter of whatever we're dealing with, okay? So on a numbers basis, because we are doing a chemical comparison here, we have to do the numbers rather than mass. Molar basis, C, concentration of C in moles per liter to the raised to the C power. Most of the time, it'll be simple cases, and these will just be 1, so that's convenient, times D to the D power, concentration of D, divided by concentration of A to the A power, and the concentration of B to the B power. Now, there are 2 little caveats here. When we have scenarios where we have a pure solid or a pure liquid, we're going to count those concentrations as unity, as 1. If we were to, let's say, consider the concrete in a swimming pool that lines the swimming pool, and it dissolves just a tiny, tiny bit, and it's going to reach equilibrium. That concrete, whatever mineral is there that's dissolving, there's so much mineral there that it's kind of infinite in some way, and so we're going to define that as just 1, a concentration of 1, because it's a solid. We're going to do the same thing for a liquid. So if we want the the concentration of H2O, technically, yeah, we could go solve that. It's like 55 moles per liter or something. But we're going to say that that's just going to be 1. And in the context of an equilibrium reaction like this, that's all we need it to do when we're referring to it that way, as a liquid. Okay. Yeah, and I already had that written up, so you got it. Okay, so with those 2 little caveats, this is it. This is all we need to know for the equilibrium reactions. We have some number, some equilibrium value that defines the ratio between the products and the reactants. Okay, you saw actually that video using this slide. We're really considering the scenario once we've found the equal rates. And just as a reminder, as he was going to go on to say probably, the amount of stuff can be different, but the fact that they've stopped changing, that's the important part, right? So we're going to reach an equilibrium where there's some amount of them. It's not that the amount is in equilibrium. It's a little bit more like a seesaw where you get a balance of the weights on either end, and that's your equilibrium. There might be more on one side than the other, but you found the equilibrium. Okay, you'll see this a lot as a pH diagram where we plot pH on the x-axis and the fraction of some molecule on the y-axis. So here's fraction, in this case, the carbonate system. And what you'll find is you have an equilibrium reaction between H2CO3 that will be in equilibrium with H plus HCO3 minus. So that is shown right here. That equilibrium, at that point where they meet, we have equal concentrations, and we can assess that from our equilibrium equation in a moment. But basically, this whole area where these 2 are interacting, that's the H2CO3 in equilibrium with HCO3 minus. So depending on our pH, we're balancing that equilibrium differently. And I'll show you that in a moment. That'll make a little more sense. We also have HCO3 minus in equilibrium with H plus and CO3 2 minus. That's these 2, right? So the bicarbonate, HCO3 minus, is in equilibrium with 2 different species. The H2CO3 basically becomes irrelevant up around neutral pH or so. It's a very, very tiny fraction of solution actually has that. Most of it's in HCO3, and then as we raise the pH higher, most of it becomes in the carbonate. Okay, so from this, if we look at, let's say, the equilibrium for the first one, if this is the first one and this is the second one, then the first one would look like this. We said products over reactants, right? That was our equation. So let's just write that up real quick just to get a feel for what that looks like. So we would have the products, H plus times HCO3 minus. Both of these are to the power of 1, thankfully. And that would be divided by H2CO3. That would be our first equilibrium reaction. And if you notice, this has a dependence of H plus. And if we change the H plus, that's changing our acidity, that's changing our pH. That's meaning we're going to have more or less of this stuff. So if we have a very high value of H plus, we can see in this equation here, if K is a constant, that keeps the same, and we decide to change H plus, the other two will change to accommodate it, right? The ratio between HCO3 and H2CO3 and HCO3 minus, that ratio will change when we shift the pH. It has to, because this equilibrium constant is a constant. So if we have control over H plus, which we often do, we will cause a change in the ratio of these other two things. Okay? The same thing would happen with the other equilibrium. Okay, I'm going to wrap up on the equilibrium of water and really getting into what is pH here. Okay? So the P in pH is actually just a reference to kind of, it's like a function. It's saying, hey, let's take the negative log of this thing. And we'll call that, instead of saying the negative log, we're going to say P. So we could do POH, that'd be the negative log of OH. We could do the P of X, that's the negative log of X. So when we have our water equilibrium reaction, this is H2O, as mentioned earlier, in equilibrium with H plus and OH minus. We have a K defined and well known for this reaction. And remember, the water on the denominator, this is going to be 1. So we defined this guy, the concentration of liquid water, as 1. So Kw is equal to the products, OH minus times H plus, divided by 1. And we know that's equal to 10 to the minus 14. So that means if we have neutral pH, which we say is pH 7, pH goes from 0 to 14. If we say that pH 7, and by the way, the reason it goes to 14 is right here. If we say pH 7 is neutral, that means that we have the same amount of OH minus and H plus. And by the way, because the combination of OH minus times H plus has to be equal to 10 to the minus 14, then we know that at pH 7, that H plus squared is equal to 10 to the minus 14, right? Under that condition, we substitute one for the other. We could say OH squared, H plus squared. That means that at pH 7, H plus is equal to, surprise, surprise, 10 to the minus 7. And this would be moles per liter, right? This is the brackets. So when we say negative log of H plus equals 7, that's the same thing as saying pH 7. And so if we were to put in the negative log of 10 to the minus 7, we should get 7 back as our value. All right, so that's all right here. We'll pick up there next time, and see you guys on Thursday.